Welcome back, everybody. This is our 12th session in JEE Mains previous year questions for chapter Moving Charges and Magnetism of class 12th. Before this video, we have taken 11 sessions in this series for this chapter, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years, so you can go to our channel's playlist section and find those videos also. And if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any donation amount will be highly appreciated. So with this, let's start today's video. As in the previous one, I think we were around 80, question number 80. So that was the last one which we solved, and today we will start with 85. So let me adjust pen thickness and on the screen. So let's start. Now, a wire carrying current I is tied between point P and Q, is in the shape of circular arc of radius r due to uniform magnetic field perpendicular to the plane as shown in the paper. Means magnetic field is in the negative z direction. If we assume here x is like this, if we assume that this is x, y and z, so means here magnetic field is in the negative z direction. In the vicinity of the wire, if the wire subtends angle 2 theta at the center of the circle of which it forms an arc, then the tension in the wire. So we have to find out tension in the wire. Now suppose first of all, let's find out the force on the wire, that what will be the amount of force acting on the wire. So we know that force on a current carrying conductor, and here direction of the current is not given. So let's assume that current is in clockwise direction. So force is equal to I L cross B. Now, as magnetic field is into the page, so we need to have the value of length that is in x-axis. Because why in the x-axis? Because we need to have the value of the length which is perpendicular to magnetic field. So here we can have value of length perpendicular to magnetic field in the two ways. As our magnetic field B is in minus z direction, so our length can be either in positive negative x direction or positive negative y direction, and that direction will be decided by the direction of the current. As we can see here that prominently current is in the x direction. Yes, there is y component also. You know that current is not a vector quantity. Here current is prominently flowing in the x direction, and length is also prominently in the x region. So what we will do here, we will take length in the x direction, and that should be a straight length, because in cross product what we have I L B sine of theta. We want this theta to be 90 degrees so that we have maximum force available. So what we will take, we will take this value of the length, that straight distance between P and Q. Now to find this value, as it is mentioned that this radius, suppose this point is O, so OQ is equal to R, and if I add a point here, suppose D, then QD will be r sine theta, and PD will also be r sine theta. So then I can say that length is equal to twice of r sine theta. Now our length is in x direction and magnetic field is in negative z direction, so angle between them both of these is 90, and we will take this as phi, as this phi is the angle between length and magnetic field, and this theta is the angle between this vertical line and the we can say OQ line and OP line. So these two angles are different. Here phi is 90 degree. Why 90 degree? Because length is in x and magnetic field is in the negative z direction. So total force comes out to be sine 90 will be 1, and we will have I 2r sine theta into B. So we can say 2IRB sine theta. This will be the value of the force acting on the wire, and direction of this force will be, as direction is decided by L cross B, length is in I and magnetic field is in minus K, so it will be I cross minus K. So we can write it as K cross I, and from this we can say direction will be in the J direction, or magnetic force here will be acting in the upward direction. So let us draw that. Suppose this is the magnetic force acting in the upward direction on the wire, and this force F will be acting on the whole wire. So I only represented at 2 points P and Q. It will be acting also in the some way, some point between. So it will be acting on the whole wire. Now let's suppose there is tension T in the wire. Let's suppose there is tension T in the wire such that, because at this point wire is extended like this, so tension will have this direction, and similarly on the point Q tension will have this direction. Now we can resolve tension in the two parts further. So let's say this will be the one component. Okay, let me choose this different color for better contrast. This will be one component and this will be the another component. Similarly here and here. Now coming to the angles, that what will be the angles here. Now as this angle is theta, and if I draw a line here, if this angle is theta and I draw a parallel line here, then this angle must be theta. Then this angle will be 90 minus theta. So this angle will be 90 minus theta and this angle will be theta. Similarly here, this angle will be theta. This is T tension, this is tension T. So we have T cos theta here and T sin theta downwards. Similarly, T sin theta here and T cos theta here. Now these T cos theta and T cos theta are in opposite direction to each other, so they will cancel each other. And T sin theta, both of these T sin theta are in the downward direction or in the negative J direction. So total downward force will be 2T sin theta, and total upward force due to magnetic field will be 2IRB sin theta. So sin theta get cancelled, 2 get cancelled, and tension in the wire will be IRP. So this will be the tension, option C. Now some of you can say that sir, we assumed that direction of the current will be in the x direction. What will happen if we assume the direction of the current is opposite? That can come into your mind. Then if direction of the current is opposite, then here our length will be in the negative I direction, and then the magnetic force, this F, will be in negative Z direction, or we can say downward. Then this magnetic force will be downward. Then what will happen? Then this we can say this wire, which is in this example is curved upward. In that case, this wire will curve downward, because here we are assuming that these 2 points of the wire P and Q are fixed. These 2 points are fixed. And now if on a straight wire, suppose we have a straight wire with P and Q are fixed, and if we applied force, downward force, then it will stretch downward, and there will be some wire will look like something, and now tension will be upward. So now this tension force will be in upward direction, and it will again balance the magnetic force. So that will happen. So uh, you can get an idea of the direction of the current from the stretching of the wire. Now moving to the next one, and how they are fixed, and it is already mentioned that it is tied between the point P and Q. So moving to the next one, a conductor lies along Z axis at minus 1.5 meter with Z 1.5 meter and carries a fixed current of 10 ampere in negative Z direction. So current is in downward direction, and conductor is between minus, so these are the limits of the conductor, of the length of the conductor. For a magnetic field of this value, find the power required to move the conductor at constant speed x. Constant speed to x is equal to 2 meter, y is equal to 0 meter in 5 into 10 raised to power minus 3 second. Assume parallel motion on the x-axis. So we have a conductor here, and we have to move this conductor from this point to this point. There is a magnetic field acting, and we have to find out the power. So basically, as we have to find out power, we know that formula for power is dot product of force and velocity. Force here is the minimum amount of force that we will apply, and V is the velocity. Now let's focus these two variables, force and velocity. First, go with velocity. As we know that, as per mentioned in the question, that velocity is constant. We know the distance which needs to be traveled in the x direction, and we know the time given. So we can find out velocity will be distance by time, that is 2 divided by 5 into 10 raised to power minus 3, that will be 0.4 into 10 raised to power minus 3, or 4 into 10 raised to power minus 4 meter per second. So this is the value of the velocity required. Now coming to the force value, as this is a current carrying conductor in some magnetic field, so force on this conductor due to magnetic field, this is not the force which we are applying, this is the force due to magnetic field. It will be I into L cross B. So here current is, I think, yes, 10 ampere. Now length, as current is in downward direction, so this length of the conductor will be taken in the negative Z direction, and length will be 1.5 to 1.5 on the both side of the axis, so it will be 3. And assuming here we are taking this our axes are in the units of meters, so length will be 3 meter in the negative Z direction, or minus k. And cross product with the magnetic field, that is 3 into 10 raised to power minus 4 e raised to power minus 2x with direction is given into unit vector in j direction or y direction. So it will be in the j direction. So solving these, we will get 30 into 3, 90 into 10 raised to power minus 4. So 90 into 10 raised to power minus 4 into e raised to power 0.2x with minus k cross j. Now we know that k cross j is x, or sorry, we can say I. K cross j is I, and with negative sign, so we will have minus I sign here, and it can be further written as 9 into 10 raised to power minus 3 e raised to power negative 2.x with negative I sign. It means that magnetic force due to magnetic field will be acting on this conductor in the negative x direction, opposite to the uh, movement which we require. We require this conductor to move in positive x direction as per the question, but when we calculate the magnetic force, that magnetic force is acting in the negative x direction. So it means we need to apply this amount of force, minimum amount of force that we require to apply is this one, so that conductor should not move in the negative x direction, and we have to apply some extra somewhat little amount of little amount of extra force, so that it start moving in the positive x direction. So minimum amount of force that is required to be applied is this one, and velocity is this one. So we can directly calculate the power, as we know, formula is force times velocity. But we have a problem here, as we can see from this formula, that as from this value of the force, that here force is variable. It depends upon the value of x. Value of force is not constant. Value of velocity is constant, but value of force is not constant. So we cannot directly apply this formula. What we have to use? We have to use method of integration. So then we will use dw is equal to f dot dx. We will integrate dw from x 0, starting from 0 to 2, and this will be f dot dx 0 to 2. This will give us w, or the work done, total work done. Integrating this side, now we will remove the direction because its part is done. So we will have 9 into 10 raised to power minus 3 integral with 0 to 2 limits e raised to power minus 2 point x dx. This will be the integral. Now solving this, we will get 9 into 10 raised to power minus 3 e raised to power minus 0.2 x divided by negative 0.2 with limits 2 to 0. And we have a negative sign here, so negative sign we will also take. So it will become negative negative positive. This will be 2 by 10, so 9 by 2. Here we will have 10, so 10 raised to power minus 2. Putting values of x here, so it will be e raised to power negative 0.4 minus e raised to power 0, or minus 0. Minus 0 will be 1. So this will be 4.5 into 10 raised to power minus 2 e raised to power negative 0.4 is 0.67, and e raised to power 0 is 1. So what we will be left with? We will be left with, solving this part, we will have 1.45 into 10 raised to power minus 2 with negative sign. So this will be the amount of work that we need to do. And from this we can calculate the power. How we will calculate the power? We know that power is rate of doing work. So it is 1.45 into 10 raised to power minus 2 divided by the time given is 5 into 10 raised to power minus 3 seconds. So it will comes out to be 0.29 into 10 raised to power 1 or 2.9 watt. And here is option B will be the right answer here. Moving to the next part or next question. Three straight parallel current carrying conductors are shown in the figure. The force experienced by the middle conductor of length 25 centimeter is. So we have to find out force for the middle one. Now if we see here that here in the both of the outer conductors carries current in the upward direction and the middle conductors have force current in the downward direction. So this conductor will apply a repulsive force on it, and this conductor will also apply another repulsive force on this, and we have to find out their vector sum. So this is conductor A, this is conductor B, and this is conductor C. So we know that force per unit length on a parallel conductor, parallelly infinite long straight conductor, will be mu naught by 2 pi I1 I2 by d, or force is equal to mu naught I1 I2 into length by 2 pi of the distance. So now force between B and C. Force between B and C. Here magnetic field will be produced by the conductor B and force will be experienced by the conductor C. So it will be mu naught 2 pi into value of I, that is 30, and I2, that is the current in, sorry, I into I1. I1 that is 30 and I that is 10 into length that is 25 centimeters. So 25 into 10 raised to power minus 2 divided by the distance that is 3 centimeters. So we will get that is mu naught by 2 pi into 2500. We will do further calculation after their vector sum. Now force between A and C, that will be same again, mu naught by 2 pi into currents, here we will have I2 into I, so 20 into 10 into length into divided by the distance, that is 5. So 10 raised to power 2 cancelled and 25 cancelled, so this will be 200 into 5, that is 1000. So mu naught by 25 into 1000. So we can say repulsive force of BC is greater, means force acting in the right side here. BC is acting in the right side, so force acting towards the right is greater, so net force should be towards the right. So and we have to find out value, and all the answers are towards right. So net force will be their subtraction, so it will be mu naught by 2 pi into 1500, and it will be 4 pi into 10 raised to power minus 7 divided by 2 into 1500, so 2 pi, sorry. So it will give us 2 and 3000 into 10 raised to power minus 7, and further 3 into 10 raised to power minus 4 Newton towards the right. So option A will be the right answer here. Moving to the next one. A rectangular loop of wire supporting the mass m hangs with one of the uniform magnetic field B pointing out of the plane of the paper. So magnetic field pointing out, so it should not be pointing outward, it should be pointing inward, because as per the cross we have field in inward direction. Clockwise current is flowing such that I is greater than mg by ba, where a is the width of the loop. Then the weight rises due to vertical force caused by the magnetic field and the work done on the system. Weight do not rise. Weight rises due to vertical force caused by the magnetic field, but no work done is done. And weight rises due to vertical force caused by the magnetic field and work is extracted from the magnetic field. So let's slide it down slightly, and let's first discuss regarding the directions and the force. Here, as we can see from the diagram, that PQ is the part of the conductor that is inside the magnetic field, and inside the length of the PQ, we can say length of the conductor PQ will be, suppose L, assuming length is L or A. If, let me check out if it is mentioned or not. Rectangular loop of wire. Okay, it is mentioned in the diagram that length is A, so it will be A. And here direction of the current is in clockwise direction. So current in PQ conductor is moving in the positive x direction. So here we will have I unit vector. And magnetic field, as per statement, it is pointing out of the plane of the paper, it means in positive z direction. So magnetic field, we can say, is B into positive k. So if we find out the magnetic force, it will be I L cross B, that will be I A B, and I cross K we know is minus J. I cross K is minus J. So magnetic force according to this scenario will be in the downward direction. So hence in this scenario, by default weight acts downward and magnetic force is also acting downward, means this part is wrong of the statement. Pointing, it should be into the plane. And as we can see from the diagram that magnetic field is into the plane, so it is in negative k direction. If it is in negative k direction, then we have I cross negative k, that will give us positive j. So now our magnetic force is in the upward direction. Now our magnetic force is in upward direction, and now weight or this mg in the downward direction. So for balance, I A B should be equal to mg, and from that we can get I is equal to mg by AB. If we have this value of current, then this whole system will stay in balance. But if value of current exceeds, if value of current I is greater than 1, is greater than this value, if value of current is greater than this value, then what will happen? This side will increase in amount or in magnitude. And if this side will increase in the magnitude, then we can say magnetic force will be higher. And if magnetic force is higher, then what will happen? The weight will rise upward until not until, it will keep on rising. Weight will keep on rising because as mg is already constant, and until this loop enters in the magnetic field, it will keep on rising, and it will stop only after this loop reaches completely inside the magnetic field. Let me draw a loop here. Suppose this is our loop at right now, at this is at this position. As we can see that magnetic force acting upward on this loop and downward mass is constant, mg is constant, so we will have net upward force. So this loop will keep on moving via acceleration, and when the lower part of the loop reaches inside the magnetic field, assuming at this point upper part is also in the magnetic field, now what will happen? As in the upper part, direction is in positive current is in positive x, and in lower part current is in negative x. So now here we will have Fm acting on the upward, and here we will have Fm acting in the downward, and we have also mg here. So now what will happen? This will start moving downward, and as it start moving downward, again this lower part comes out of the magnetic field, and again upward force becomes greater, so it will again start moving upward. So it will start oscillating after the whole loop reaches into the magnetic field. So now as we have to only discuss with the one part in the magnetic field, so it will rise up. So in option A it is rising up, in option B it is not rising up. So option B is cancelled, and in C it rises up, and in D it also rises up. So now in the option C it is mentioned that weight rises due to vertical force caused by the magnetic field, but no work is done on the system. Now it is mentioned that no work is done on the system, and if we can see that this mg mass is going upward. Suppose this was the initial position of the mg, and now it has reached to some another position. So what it has gained? It has gained potential energy, and if it has gained potential energy, that energy has to be come from somewhere. So work needs to be done. So there is work. So option C is cancelled. So if there is some work done, then this work has to be done by some force, and we know the only force here that is acting against the mass, that is magnetic force, and that is that force is acting due to magnetic field. So the work is done on the system, but with the help of magnetic field, or we can say that work is extracted from the magnetic field. So option D will be the right answer here. And now some of you will remember that in some questions where in the circular motion, when some charge particle start moving in the circular motion, in that case we said that magnetic field does not do any work. The work done by magnetic field is always zero in the circular motion, and that happens because in that case the force, magnetic force acting, is always acting perpendicular to the velocity or the motion. But here we can easily say that velocity is also upward, as mass is moving upward, and magnetic force is also moving upward. So here we will get some power out of this, and if we are getting power, then it means there is some work done on the system by the magnetic field. So with this, we end this video here. Hopefully what we have covered till now is helpful to you. Again, if you have any doubts or suggestion, you can put them in comment section. I will try to resolve them and implement them. And if you like these videos, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you would like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.